Good afternoon. It is June 22nd, 2016, and here we are for another lovely day of ENGR 2301 Engineering Statics. So, let's get going. Alright, so we're going to follow the same format as previously. We're going to first work through a few example problems from the previous homework. From the Beer Vector Mechanics book. Then we're going to move on to some new theory, and then we're going to move on, and then we're going to finish up with some example problems on the new material. The new material for today is to finish up our discussion of basic structural engineering, at least in terms of frames, the study of frames. We've looked at trusses, and now we're going to look at simple structural frames. And we will learn exactly what a frame is and what distinguishes a frame from a truss, and we will learn how to work with some very basic frames here. If you'd really like to work with frames, major in civil engineering and take my course, Civil Engineering 3325, Structural Analysis, and I can teach you all sorts of tools to analyze very complicated frames. Or if you really want to go crazy, go ahead and enroll in graduate school in Structural Analysis, and you can just slowly lose your mind. Okay. As a matter of fact, yes, I did study that in grad school. Why do you ask? Yeah, probably quickly lose your mind, right? I don't have to worry about losing my mind anymore. I lost it long ago, so that's okay. The great thing about being crazy is that it only happens once. Okay, anyway. Oh boy. Okay, so what do we have here? Problem 6.51. A stadium roof truss is loaded as shown. Determine the forces in members AB, AG, and FG. So, first of all, let's see what we're looking for. We're looking for AB, AG, and FG. So, what options do we have? Well, we could use this section here. Again, we're using the method of sections, so we could use this section here, perhaps. But then we'll have to deal with the reactions, and there's 4 reactions here. We're going to have to solve for those. That's just going to be a bit more work, and it's doable, but why bother? I'm looking at this, and I'm seeing a very clear solution. I'm just going to cut out this portion right here. So, cut out this section with a nice UT Tyler orange here. And this is the section that I'm going to consider. Remember, the whole basis of the method of sections is that let me back up. The whole basis of the method of sections is that if a structure or an object is to be in static equilibrium, then any piece of that object must be in static equilibrium. So, for example, the goofy example I gave yesterday of the person drawing free body diagrams of various body parts, that works. Or we can consider a more mundane example of a structure, and we can divide it into pieces and do free body diagrams of each piece. And every time we have a member that crosses the boundary, we will have to represent the forces that are inside that member. So, let's see here. What I'm going to do is I am going to draw a triangle BGD.
Why do you choose BGD and not what you cut, include what you cut?
The question was why, someone asked, why am I doing triangle BGD and not the things that I'm cutting into? I'm only going to draw the members as forces. They're not going away, but they're going to be drawn just as forces. And notice that I'm not bothering to even draw any of the interior members because they're not important for what we're trying to find. All we're concerned with is this force, and this force. So I'm just going to treat this as a block, as a single rigid body. So this is TAB, or not TAB, FAB, using the system we have previously developed. So let's see, this is FAB. FAB. This is let's see, FGA, FGA, and FFG. And FFG here, like shown. Now we will need our force triangles. Oh, we also need to show any other forces on here, and that's going to include our 1.8 kip force here, 1.8 here, and 0.9 here. 1.8 kips here, 1.8 kips here, and 0.9 kips here. Okay, I'm going to put some labels on it. This is B. This is G. And this is D. Then, let's see, we'll need our force triangles for these. So let me just draw them to the side here because I'm kind of scrunched there. So FAB is going to have a force triangle, let's see. Well, let's see. To me, that looks like it's going to be, again, force triangles. We're not concerned with only that piece. We're concerned with a lot. We're not really concerned with the piece. We're concerned with the angle. So I'm going to use 28, 40, 40, and 9. Huh? Oh, what? Huh? The hypotenuse is 41? Okay, I'll double check it, but that sounds about right. Square root of 40 squared plus 9 squared. Yep, 41 exactly. 41 here for our FAB. And then for FGA, let's see. So I'm just going to label this force triangles. FGA. This is going to be 12. This is going to be 9. And this is going to be, well, this is a 3, 4, 5 triangle, isn't it? Huh? Let's see. Yes, this is a 4, 3, 5 triangle. All right, questions so far? Okay. So, let's see. We need to find creative, questions? Okay. We need to find some way to get at the solution. Now, what could we do? I would like to take moments about creative places in order to end up with equations with only one unknown in them. So I think what I might do, which will be a bit unusual, is I think I'm going to first sum moments about point D. See, FAB is going to it will not generate a moment about point D, simply because its line of action passes through point D. FG will likewise not generate a moment about point D because its line of action also passes through point D. But FGA will. It will have an X and a Y component. Oh, actually even better, FGA's its x component will not generate a moment, but its y component will. So this is going to be incredibly easy to solve for the moment there. Solve for the force in FGA. Oh, sorry. Let's see. Sum of moments about point D, counterclockwise positive. So I'm going to have FGA, only the y component of it though. FGA times, and the y component of this is going to be 3 over 5. And this is going to be negative because it's a negative moment about point D. Then I'll have, oh, and I need, derp, I actually do need my distance here, my moment arm, and that's going to be times 28 feet. 28 feet from G to D. Then I'm going to have plus 1.8 kips, also times 28 feet. Then plus 1.8 kips times 14 feet equals 0. To make my life a little simpler, I'm first going to just divide across by 14, just to make that a little bit simpler. And so then FGA, and that becomes a 2, let's see, is going to be 1.8 times 2, well actually 1.8 times 3 is what, 7, no, 5.4? 5.4, yeah, that makes sense. So yeah, 5.4. So this is going to be 5.4 kips. Combine these together, bring them over here, multiply by -1, times 5 over 6, if you can follow my crappy algebra. And I'm getting 4.5 kips. And it's positive, so it will be in tension. And we have our first unknown, or our first solution. Questions on how I did that? Okay. Again, what I did was as a reminder or as a review, I cut out the section that would get us the desired values with as little fuss as possible. Then I summed moments about a point that would eliminate everything but one unknown. And that's the ideal. Sometimes you can't do that. If the forces are arranged in certain particular ways, there's no way around that, especially if you have parallel forces and things like that. But whenever possible, I try to do that. Okay. So next, let's find some other points of some moments about. Perhaps if I summed forces about point G here. That'd work well. So I'm going to do a sum of moments about point G. What will that do? Let's observe. FGA and FFG both have lines of action that pass through point G. Therefore, neither of these will generate a moment about this point. The y component of this force will not generate any moment because its line of action also passes through point G, but the x component will. So again, this will allow us to very quickly jump to this force, FAB. Okay, so let's do that thing I said. All right, so, uh-oh, we got a problem. What is that problem, do you know? We need to know this vertical distance from B to G. So we're going to need to use some similar triangles, yes?
We could also sum it about A, and you wouldn't worry about that.
If we summed about A, we wouldn't have to worry about that. I'll do that when I get FG, I think.
Okay.
But for this one, I think, yeah, we do need to get I want to get the vertical distance from here to here, and that's just a matter of similar triangles. So let me call this I'll call this distance Y for lack of a better word for now. So setting up a ratio, Y over 28 must be equal to 9 over, let's see, 28, 40. This is just basic geometry, algebra, whatever you call it. 9 times 28 over 40, similar triangles. And I get 6.3 feet. 6.3 feet. Good, good. Now, let's do this. So I'm going to have FAB times the horizontal component, or I need to get the horizontal component, which will be simply the ratio of 40 over 41 from here, times a moment arm length of 6.3 feet, which we got previously. Then this force, and this force will not have any effect there because their lines of action pass through point G. Then minus 1.8 kips times 14 feet minus 0.9 kips times 28 feet. And let's see, the rest is just math. So let's see, 1.8 times 14 plus 0.9 times 28. So let's see, then 40 over 41 times 6.3. So I get that 6.146 FAB is equal to 1.8 times 14, 0.9 times 28, 50.4. And this leads us to the FAB. This leads us to that FAB is equal to 8.2 kips. FAB is equal to 8.2 kips precisely. And then finally, the only unknown that we still want to solve for, I mean, there's plenty of unknowns. There's lots of different member forces that we haven't solved for and we're not going to solve for. But in terms of the ones we really want, the only one left is FFG. So again, notice the method the hardest point about the method of sections is choosing the right section. And so again, notice what I did. I marked with a line each of the member forces that I want. And then I made sure my cut went across those, and also didn't generate a bunch of extraneous unknowns if possible. Okay, so now we need FFG, and we could do this any number of ways. We could sum moments about point A, that would be very convenient. We could sum forces in the horizontal direction, that would be less convenient. So I think I'm just going to do a sum of moments about A, because point A is up here. These both intersect at point A, so they won't generate any moment about there. So it'll be fairly easy to sum moments. Sum of moments about point A. All right, so I'm going to have FFG. Now FFG is going to generate a negative moment about point A. Negative FFG times a moment arm length of 9 feet. 9 feet vertical from here to here. And then all this junk is going to be generating moment. Plus, oh, actually, let's see here. This is generating negative moments, and these are generating negative moments. Uh-oh. That's okay. It's obviously just in compression. Well, maybe I shouldn't use that word, obviously. That's a dangerous word. Minus, actually, we need to consider, okay, that works here. Minus 1.8 kips times 12 feet. Minus 1.8 kips times, that looks to me like 26 feet. Minus 0.9 kips times 40 feet. And that'll equal 0. All right, so now I just throw this in my calculator. It's fairly easy to solve from here. 1.8 times 12 plus 1.8 times 26 plus 0.9 times 40 times 12, 1.9 times 26, and divided by 9. And FFG is equal to negative 11.6 kips compression. Like so. Questions on that? Could I have summed the moments on the x direction? Oh yes, I could have also summed the forces in the x direction. Yes, that would have worked just as well. It would have been just a little bit more. Well, I think it'd be a little more work because we'd have to break these into components. But then in turn we wouldn't have to have these things in the expression. So it's probably 50-50 either way. About as difficult either way. So yes, the sum of forces in the horizontal direction would have worked just as fine. All right, other questions?
You didn't do a force triangle for FFG?
Force triangle for FFG. Okay, no, a force triangle is not necessary for FFG because it's perfectly horizontal. Yes.
For the moment around G, how did you know that you would need the x component of FAB?
Okay, the question is for the moment about point G, how did I know I would need the x component of the force FAB? Well, look at this force here, FAB. It has a y component like this and an x component like this. Its y component passes right through point G. So its y component will not generate a moment about point G, while its x component will. Now, alternately, if we really wanted to bang our heads against the wall, we could just create vectors for all these things and create vectors for the r's and do cross products and all of that. But I don't feel like doing that if I can avoid it. So you've all seen what that's like, and I try to avoid that if I can. So, other questions? All right, moving right along. Okay, the truss shown was designed to support the roof of a food market. For the given loading, determine the forces in members FG, EG, and EH. So the first thing I'm going to ask myself is this thing symmetric? It looks like it's sort of symmetric, but then if I look closer, is it symmetric? Let's see. Yeah, it looks symmetric, doesn't it? Yeah, it is. See, these are talking about this dimension here, 4.8 is talking about this line here. And yeah, if it wasn't symmetric, if it was not symmetric, they would need to provide different dimensions. Huh? It might help, might not. I just wanted to know it. Okay. How it might help is that if we need to get the reactions, it's going to be very easy to find the reactions. And actually, we will need the reactions, or at least one of them, because there's no way we can cut this without including a reaction end. The other problem had a cantilevered end, so we could actually cut it without having any reactions. But this truss here, there's no way we can cut this without having at least one reaction. Well, I mean, sure, I guess we could cut it like this, but then we're introducing like 6 unknowns, and that's going to be unsolvable, so let's not do that. Okay, so what's my first step? Yeah, find my cut. And I'm going to do that by first marking what I want. So FFG, there we go. I want that one. EG, I want this one. And EH, that one. Well, that makes my job of finding a cut very easy, because I'm just going to do this thing here. Makes as much sense as anything. Now, I am going to use arguments of symmetry to get FAY, or just AY, I should say. AY. There's also an OY over here, but I'm not concerned about that. There's also an AX, but that's obviously 0. There's no horizontal forces applied to this truss, so we don't need to worry about it. Okay?
You add up all the forces divided by 2.
Exactly. AY by symmetry by symmetry, AY is simply going to be equal to, let's see, 0.6 plus 1.24 plus 1.04 plus 1 plus 1.2 over 2. And that's it. I just added up half of the forces. So let's see. I'm feeling lazy, so I could probably do that in my head, but I'm feeling lazy today. Plus 1.04 plus 1 plus 0.6. And I get 4.48 kilonewtons. AY is equal to 4.48 kilonewtons. So again, just based on arguments of symmetry, if I did not have a symmetric system and I needed the reaction here, I would just use balance of moments to find my reaction there. I would probably sum moments about O. Okay, so let's draw this thing. Let's see, let's draw this beast. Again, I do not care about the internal stuff here. All I care about is the forces here, here, and here. So I'm just going to do a very rough drawing of the section. Yes?
Why is AX 0 again?
Ah, AX is, the question was, why is AX 0 again? The reason it's 0 is because there are no horizontal forces applied to the truss. If there were horizontal forces, then it would not be 0, and we would need to take that into account. But good question.
Horizontal external.
Yes, horizontal. Yes. I should rephrase that. Horizontal external forces. There will definitely be horizontal forces present, but they are horizontal internal forces, not horizontal external forces. Okay. So I'm going to draw a really crappy truss diagram here. So we have B, D, and F. Then I'm going to come down here, and we will have E. And I don't care about any of their stuff inside there because it doesn't matter. And then I'm going to draw some forces on here. They're trees, happy trees. F, FG, FEH, and I'm going to try to draw this thing big enough so I can include the force triangles on this. FEH, we will not need a force triangle for that. And let's see, FEG. All right, so let's get some force triangles. For FEG, let's see, the base is 2.4. The height, G, let's see, where is G here? Well, that's no fun. I guess we might actually have to use triangles to force, or we might actually have to use proportional triangles to figure that out. I believe. Yeah, that's no fun at all. Yeah, we don't actually have the exact dimension to G. Isn't that lovely? So we're gonna actually have to use a little trigonometry to figure it out. I need to know the distance from F to G, basically. So basically from F to I, this is a constant beam of constant slope. And from, let's see, so let's just call this, this is a y here again, basically. Y over 2.4. Y over 2.4. Oh, wait, sorry, no, over, no, that'll work, yeah, y over 2.4 equals 1.75 over 4. Oh, derp 5. 2.4 plus, oh my gosh, I cannot math today. That is 6. 2.4 plus 3.6 is 6, if I can math properly. And so y will come to 1.75 times 2.4 over 6 comes to 0.7. So the vertical distance between F and G is 0.7. That's what I was doing there. 0.7. And then I just get the hypotenuse. Huh? It's 2 point, yeah, it's, but what that comes to is 2.5, but yeah, it's a 720, yeah. Okay. There you go. That comes to 2.5. And then, oh wait. I think I got that screwed up. I got that mixed up. I put this thing on the wrong one. Sorry. Derp. Helps if you're at the right force triangle on the right force. 0.7, 2.4, 2.5. There, that makes me happy. Did I get it right this time?
So this is the triangle for FFG.
Yeah, this one is for FFG. Okay. And here. So now for now on FEG though, the vertical distance is going to be, let's see, it's going to be 4.8 plus the 0.7, so that's going to be 5.5. And the square root of 2.4 squared plus 5.5 squared is 6 exactly. Well, approximately. Huh?
How does it get 5.5?
5.5, I added, see, the vertical distance from F to G is 0.7, right? And the distance from E, the vertical distance from E to F is 4.8. 4.8 plus 0.7 is 5.5. And this comes to 6.00. It's not exactly 6, but it's 6 to basically 3 zeros. 6.001, essentially. All right, now that that is out of the way, the rest is cake, right? Then we'll have our 4.48 kips.
It's drawing the triangles that
Huh?
drawing the triangles is usually where I mess up.
0.6 kip. Oh, these aren't kips, these are kilonewtons. Kilonewtons. 0.6 kN. And 1.24 kN. And then our, let's see, that looks like 1.04. 1.04 kilonewtons. Although I don't think we're probably going to need that one. Well, we might, depending on where some moment's about. Okay, so now we're ready to go. And let me just point out where let me just show where point G is also on here. Point G is here, and the distance here, the horizontal distance again is 2.4, and the vertical distance, which we've already calculated, is 5.5. Just in case we need that, or actually let me just call this, label it like this, 4.8 and 0.7. Okay, and that should be good for what we need. Now, let's see. We have 3 unknowns, and we can just get them by taking moments about clever locations. So I'm going to start by, let's say, I will sum moments, why not about point E? If if I sum moments about point E, look what we'll get. Well, this force and this force and this force will not generate any moment about that point because their lines of action pass through that point. And the vertical component of FFG will not generate the vertical component of FFG will not generate any moment about point E because its line of action also passes through there. However, its horizontal component will, and it will generate a negative moment about there. So negative FFG times 2.4 over 2.5. And that will give us the horizontal component times a perpendicular distance of 4.8 meters. 4.8 meters. Then we will have, let's see, positive 1.24 kilonewtons times 3.84 meters plus 0.6 kilonewtons times 3.6 plus 3.84 comes to 7.44. 7.44 meters. And then minus 4.48 kilonewtons, also times 7.44 kilonewtons, or sorry, 7.44 meters. And all of this equals 0 because this is statics class. Now the rest is just plug and chug. 1.24 times 3.84 plus 0.6 times 7.44. 1.24 times 3.84 plus 0.6 times 7.44 minus 4.48 times 7.44 comes to, we then have negative FFG 2.4 times 4.8 over 2.5, negative FFG times 4.608, all this reduces to 4.608, minus 24.106 equals 0, and this leads us to that FFG equals negative 5.23 kilonewtons compression. Assuming I did that math correctly, which is likely but not impossible. Okay. All right. So then we have one of the forces. Yes. The F of G. Is that in the X? It's this. It's the force itself is in neither. See, it's a force that goes at an angle. Oh, the one I used here. This is the X component. Yes, I wanted to use the X component in the moment calculation. All right, then. What else could we do? I will sum moments about. Let's see. What if I did? I could sum moments about wherever this one and this one intersect, but that's going to be at really some funky location. It's going to be like, we'd have to calculate where the intersection of this line and this line is, and I really don't feel like doing that today. So let's not do that. I'm instead going to sum moments about point G. Summing moments about G, counterclockwise positive. Let's see, so that will eliminate this one and leave us with just this one. So that's going to be, let's see. You know what, I probably should have drawn this like this, not like that. Oh well, whatever. Some moments about G is going to be, let's see, FEH. Again, at point G, FEG and FFG will both not generate any moment. Only FEH will generate a moment about that point. times a distance, a perpendicular moment arm distance of 5.5 meters. Then, let's see. Huh? It's actually positive. Positive.
Where's G on here? Where's the
G is up here. Then, plus 1.24 kilonewtons times a distance of, let's see. So that's going to be 2.4 plus 3.84. And that's 6.24. And then, let's see, then plus another 3.6. So 9.84. So plus, ooh, I forgot this one. So let me do plus 1.04 kilonewtons times 2.4 meters
is that 1.24 kilonewtons times what is that?
times 6.24 meters. 1.04 kilonewtons times 2.4 meters, and then plus 0.6 kilonewtons times 9.84 meters minus our AY moment, 4.84 kilonewtons times 9.84 meters. All of that equals 0. I'm just going to throw this whole mess into my calculator. 1.24 times 6.24 plus 1.04 times 2.4 plus 0.6 times 9.84, and then minus 4.84 times 9.84. And we get that, let's see, FEH, if you solve for FEH and divide by 5.5, you'll get that FEH, if I did this correctly, negative 5.73 kilonewtons compression.
It says tension.
Wait a minute, something's not right. Oh, derp. That's not negative. I forgot to take care of my negative. That's positive and should be in tension. Yeah, because this all of this stuff comes to a negative number. I bring it over here, divide by 5. Yeah. Tension. Okay. So finally, I am going to get my last one, FEG, simply by doing a sum of forces in the horizontal direction, because that will eliminate this force, this force, this force, and this force, and only have my unknowns. Sum of forces in the x direction is going to be, let's see, FFG times 2.4 over 2.5 plus FEG times 2.4 over 6 plus FEH equals 0. Plus FEH equals 0. Then, let's see, FFG is negative 5.23. Negative 5.23 times 2.4 over 2.5 plus FEG times 2.4 over 6 plus 5.73 equals 0. And kind of running out of room here, I'm trying to squeeze it in. Just a second. 5.23 times 2.4 over 2.5. So I will get, let's see, 2.4 over 6. I get 0.4 FEG minus 5.022 plus 5.73 equals 0, and FEG comes to, something's not quite right. I think. Well, maybe not. Oh, no, we're fine. Never mind. Negative 5.02 plus 5.73 divided by 0.4. I got 1.76. Let's see. Well, that's going to be negative. Negative 1.76 kilonewtons tension or compression.
It says -0.1476.
Negative 0.1476? Let's see what could be the origin of that. Well, we're getting slightly different answers. Does the manual can agree on our FEH and FFG?
Yes.
Okay. So let's see. Maybe we got something screwed up here. FFG times 2.4. Where? I can't. Well, no, that doesn't make sense. I'm talking about if we agree on this force here and this force here, this stuff has to be right.
Yeah.
Huh?
FEH is actually, I lied to you. FEH is actually 5.08.
Oh, okay. Oh well, whatever. There's some little error in there, but that's the general method anyway. Okay. Yes.
One last question. I know I asked
Check the
a lot.
solutions.
One
Yes.
last question. I know I asked a lot. The summit. How did you look at that jumping off point to where you looked at the picture and you realized I need to sum all forces in X direction?
You have to have a certain amount of experience at it. You have to say, what I was looking for is I was looking for a cut that wouldn't introduce a bunch of unknowns. Okay? So there can be a certain amount of experience and judgment. You have to be very careful about the cut you're going to make, and make sure that you're not going to add too many unknowns. So yes, there's still some sort of little error buried in here. So some of these aren't quite exactly right, but I don't feel like digging through a bunch of minutia right now. That's the general method anyway. There's some typo in there somewhere.
You did say it earlier. The summate. You looked at the picture and you said this and this. Why'd you choose the summation of F in the X direction? For the last step.
Oh, the question was, why did I choose the summation of forces in the X direction for the last step? Well, I could some moments about some point out here where the line DF and EH meets, but I don't want to calculate that. I would have to do some trigonometry, figure out where that line is, because you see this line here and this line here have to intersect somewhere, and they'd intersect down here somewhere, but I don't feel like calculating that today. Okay, there's that. This one here, someone was asking about, right? 6.57, looks very similar to one we did last time. This isn't the same one we did yesterday, was it? Okay. A Polynesian or dual pitch roof truss is loaded as shown. Determine the force in members DF, EF, and EG. DF, EF, and EG.
Would you design a Polynesian truss just for looks, or is there any other?
Question: would we design a Polynesian roof truss just for looks, or is there any advantage of it? I'm sure there's some advantage of it. There's probably maybe with locally available materials, there's certain advantages. I assume materials available in Polynesia, maybe whatever type of trees they have growing there lend themselves really well to this type of roof truss. I don't know. But there are certain roof trusses that are more beneficial to certain applications than others. For example, if you never use the same type of truss for different applications. Like for example, if you need to span 20 feet versus 100 feet, you're going to use different types of trusses. If you need to carry, depending on the load, if you're just talking about a roof, that's one thing. If you're talking about a heavily loaded floor that's going to need to carry 300 pounds per square foot, you might have a different type of roof truss. So really what it comes down to, the type of truss that you use to support a load or even a roof, or if we restrict ourselves purely to roof trusses, I would say how you would choose what roof truss you would use would be a function of several things. One, the span of the roof. Two, the pitch of the roof. You do need certain pitch. You do need certain pitches in terms of just rain runoff and things like that. Three, also your loadings. Uh, your loadings on a roof structure will depend on many things. It'll depend on rain load. So different areas of the country have to be designed for different levels of rain load. If you're in Houston, you got to design for a lot of rain load. If you're in Arizona, not so much. If you are up north, you have to design for snow load. You have to consider the facts that the factors. There are actual maps that you need to design for. Like you actually look on the map and where you're designing your building and saying, okay, this needs to be. You need to count for this much snow load here. Or if you, or the biggest one is actually wind. Wind, the amount of wind load on a roof, either down or even uplift, is a major factor. And that will, and wind design is a real difficult problem. You have to consider everything from how high up the structure is. Like if this roof truss is constructed above a single-story building, the load will be typically a lot less than if we're on the say the top of a 5-story building. Simply because the higher up a building is, on average, the greater the wind load, or the greater the wind speed. As you travel in the wind profile on a structure, or the winds with elevation, it does something like this. There's almost a parabolic kind of thing here, where near the ground the velocity is very low, but as you go higher and higher, the wind speeds pick up higher and higher. There's less. The reason for this is it's a fluid dynamics thing. There's friction with the ground on the wind, so it needs to be moving closer to the speed of the ground, and also there's more obstructions near the surface, so the wind can't gain speed. So the higher up you are, the higher the wind velocity you need to design for, et cetera, et cetera. So wind is a devil of a problem. It's a very complicated thing. That's an entire chapter in the ASC design code. But anyway, so the short answer is how you would pick which roof truss. Certain roof trusses would be optimized really for different types of loading and different types of spans. That's what it really comes down to.
In Houston, almost all the roofs are like 45 degrees, and that's such a steep roof for a rain load. So you say maybe a wind factor?
Could be a wind factor, yeah. The question was, someone was asking, okay, so all the roofs I see in Houston seem to be at a really steep 45-degree angle. Well, it could be a rain factor, or it could be a wind factor. Houston obviously has very high wind loads. We're in a hurricane zone here, so well, that would tend to actually increase wind load. But anyway, it's hard to say. I haven't worked with designing those myself, so I can't tell you exactly, but it would come down to wind and rain load, definitely. So, but we are in a hurricane zone, so that's definitely going to be a major factor. And Polynesian roof trusses, I guess they are very optimized for Polynesia. So, anyway. All right, what can we do? Let's see. Well, first of all, this stupid thing isn't symmetric, so we can't even do that. Joy. Although, you know what? I can do, oh wait, no, I can't do that. I thought I was going to be very clever and say, oh, force in FE, that's just going to be 400 pounds, but then I noticed this joker here, so we can't do that. Never mind. Oh well. Huh? Yeah, I'm just going to take moments about N. See, I think I'm going to go with a section like this. Let me use this section here. Like this.
Do you always take the shorter section rather than the longer to reduce the...
Question, do I always take the shorter section instead of the longer section? Generally, yes. I tend to use, when I'm doing problems like this, I generally tend to pick the shorter section, or more importantly, the section with fewer loads. So if there were if there were no loads on this side, I'd probably take a section on this side simply because there's less loads that I'm going to have to put into my calculations. So there you go. Now, in order to cut out this section, I'm going to need AY. So let's find that. So I'm going to need AY. And I am going to get that by summing moments about point N. So let's do that thing I said. Oh my goodness, this is a... Who thought of this? Man.
Skip that and do the lecture.
Huh?
Skip this and do the lecture.
Nah, but I've already started. I had to finish it. Okay. So sum of moments about point N. Trying to think if there's an easy way to do this. Not really. Okay. Sum of moments about point N is going to be equal to, the lecture today is actually fairly short, so that's okay. Well, AY, negative AY, times a distance, let's see, times a distance, thankfully they're all products of 6, but you know what, I'm going to be a little clever, which is a dangerous thing, and say, instead of using dimensions, I'm just going to use multipliers. 1, 2, 3, 4, 5, 6, 7, 8, times 8. See, all of these distances are going to be multiples of 6, right? So instead of multiplying by 6 a bunch of times, then dividing by 6, I'm just going to use the multipliers. Why not? We have 8 intervals of 6 here. And then, let's see, plus 400 times 7, plus 400 times 6, plus 400 times 5, plus 350 times 4, plus 300 times 3, plus 300 times 2, plus 300 times 1. The 200 going down on AY. Oh, thank you. Yes, I forgot. I missed my 200 there. Yes. Plus 200. I ruined my rhythm. I had this nice 8, 7, 6, 5, 4. Oh, never mind. Oh well. 200 times 8 equals 0. Okay. And so now the rest is just a bunch of ugly computation. 400 times 7 plus 400 times 6 plus 400 times 5 plus 350 times 4 plus 300 times 3 plus 300 times 2 plus 300 times 1. Well, I didn't need to do that one, but plus 300 plus 200 times 8. 400 times 7, 400 times 6, 400 times 5, 350 times 4, 300 times 3, 300 times 2, 300 times 1, and 200 times 8. And I am getting that AY is equal to 1,500 pounds. Yes.
So you did that part of the problem with your length unit as half a foot? No, wait, as 6 foot?
I effectively used a length unit of 6 feet. I effectively defined my own custom length unit and just said whatever. But I was only able to do that because this was all 6 feet, basically.
Okay.
I was just having a little fun. Okay, I don't recommend doing that on exam problems. Okay, so then AY is 1,500 pounds. Although, you know what, I thought it would be fun sometime if I was really feeling evil. Like, imagine if you took like a physics class, like, and the instructor just said, you know what, this class, you're too attached to units, so I'm just going to teach you with a custom unit system that I just came up with. And they just do like imagine if like they just build everything up, even like electromagnetism, using their own screwy set of custom units. Just like build it up like from their own definition, their own unit for mass, their own unit for length, and just build it up from there. Wouldn't that be amazing? That'd be great.
Amazingly cool.
You can only take their test. If you try to take anybody else's test, you'd be really confused.
Anyway, okay. So let's draw this section out. This actually won't be too bad, I don't think. Hopefully. Okay, let's see. Now, here. So I'm going to have this. This is going to be A, D, and C. And C. Let's see. So we're going to have F. And thankfully, this is all in the same line. F, DF. We're going to have, oh, I lied. Derp. Never mind, I'm a liar. I didn't make a mistake. I deliberately made that just to screw you guys up. Yeah, I don't make mistakes. I'm just evil. I don't know which is worse. Okay, now I'll do this kind of thing. Or the old, I was just doing it to see if you were paying attention. D, A, and E here. So this is going to be FDF, then FEF, and again we're drawing all of this as simply, we're simply drawing all of this as tension. F, EF, EF, FEF, and FEG. FEG. Then I'm going to have the, you know what, I'm going to simplify my life and say, hey, this is 1,500 pounds AY pointing up, there's 200 pounds coming down, so on net there's a 1,300 pound force here. 1,300 pounds, that's a very light load, that's not much. 400 pounds, and 400 pounds. Like so. All right, I think, what will I do here? What do I want to do? I think I'm going to some moments about point F. Yeah, that makes sense to me. Because point F here is where these meet. These meet at point F. Oh, and let me draw the force triangle for FDF here. Let me just write it up here. So here we have FEF. And the force triangle is going to be, let's see, sorry, FDF. Derp. FDF. And let's see, so the force triangle for this thing, the total horizontal distance here is 18 feet. 18, and that looks like 4.5 in the Y. And then that should be an exact number, I think. Square root of 18 squared plus 4.5 squared. Yep. Oh, nope, never mind. I'm a liar again. 18.554. 554 feet, like so. Okay. Now, I am going to some moments about point F. So what will that do? That will make it so that this force, that will make it so that FEF and FDF will not generate a moment there, giving me only one unknown. Summing moments about point F will give me the following. Well, let's see. FEG is going to give me a positive moment, and the distance here is going to be 4.5 feet. This is actually going to be the only moment expression we need to do. Then, let's see, plus 400. 400 pounds times 6 feet plus 400 pounds times 12 feet And I could do this sort of thing again if I wanted to. Plus, actually, no, I couldn't because I have this here. Never mind. Not easily. I'd have to call this like 3/4 or something, but I'm not getting that involved into it. Minus 1,300 pounds times 18 feet. Pounds equals 0. Oh yeah, I guess the UK is voting on the Brexit vote tomorrow, aren't they? Huh. That should be some fireworks. Huh?
Today,
Is it? I thought is it tomorrow or today? Huh?
Brexit vote.
Is it supposed to be 1,300? Didn't you find AY to be 1,500?
Okay, where this 1,300 comes from is I realized that there was the 200-pound force downward here, right? And AY upward here,
Oh,
and I just combined them together.
okay.
Took the net force just to make my life a little bit easier. Let's see, 400 times 6 plus 400 times 12 minus 1,300 times 18. 400 times 6 plus 400 times 12 minus 1,300 times 18. And I get that 4.5 FEG minus 16,200 equals 0. And this leads to that FEG is times -1 and divided by 4.5, 3,600 pounds tension. And we have our first solution. Next, I'm going to do a sum of 4. So that's the only moment we're going to have to do, thankfully. Any questions on what I've done so far? Okay. I'm going to do a sum of forces in the x direction. And I will get FDF times 4.5 over, or sorry, times 18 over 18.554 times 18 over 18.554 plus 3,600, which is my FEG here, equals 0. And this leads us to that FDF must be equal to, it'll be negative, it'll be compression, 3,600 times 18.554 over 18. I get negative 3,710.8 pounds, which is compression. Like so. And then finally, sum of forces in the y direction. I'm going to have 1,300 minus 400 minus 400 plus FEF plus, well actually this is going to be going downward, so I'm just going to put negative 3,710.8. That's FDF, and then the y component of it, 4.5 over 18.554 equals 0. And let's see, then FEF will simply equal, let's see here, okay, 1,300 minus 800, and then minus this times 4.5 over this. And I get that FEF is equal to, I got 400 pounds tension. Assuming I did that right. Concur? Okay. 400 pounds tension. And that's all of our unknown forces. All right, so questions on any of that? Method of sections. Solving trusses via the method of sections. All right, any other questions before we move on? Okay. All right, I think I'm going to take a short break right there, move on, and we'll come back and we'll talk about simple frames.